Hello everyone, Saqib Khan here from the Spanovation Bridge and Seismic School. I'm very happy to have all of you here joining me from all different continents and time zones. It is that time in our lives with the COVID-19 pandemic that we're practicing social distancing, and hopefully everyone is. I would really encourage all of us to practice the precautions that we need to during this time. Now, this is also the time to make ourselves a little bit better, get in better mental, physical, educational shape. So talking to you from this Spanovation Bridge and Seismic School platform, we set this up a few months ago. My partner in crime is Raj Singh. He and I set up the school, and our purpose, our real deep purpose, is dissemination of knowledge. And that's why I'm talking to you today. We're doing this series of 4 free webinars, which is going to cover a few different topics on basic seismic engineering. So today we're going to start with some fundamentals and design approaches. We'll then go into talking about the earthquake resisting systems and the equation of motion, and give you a little bit of the flavor of how the different analyses types work. Maybe we'll touch a bit upon the philosophy of deep foundation design and also detailing. But what I really want to preface this with is take your time, listen to this. We are going to upload this onto our YouTube channel. I want to make sure that the point, the knowledge gets across. I have a feeling this might be a little bit ambitious for the 4 one-hour webinars. So if there is a case where I think we're going a little bit slower than what I thought we would be doing, then I would be more than happy to just do one or two extra ones. It just all depends on how this thing flows and how and what kind of progress we're making. So thank you very much for joining me. I know that we're all from different parts of the world and different time zones. Here in North America, on the West Coast, it's 9 a.m. I know that in the subcontinent, we're probably, you guys are 12 and a half hours ahead. There may be people from Europe and South America. So again, thank you very much. The other thing I would say, and I'm gonna close my video now, but before I do that, what I would like to say is please do not try to read the slides. This is a difficult medium, and I'm going to try my best to bring my points across. It's much easier for me when I'm instructing one-on-one. I can walk into the crowd, I can make eye contact. Here, it's a little bit different. So I'm going to try and pace myself, but what I'm going to ask you to do is not to try and read off the slides. I really want you to pay attention to what I'm saying to you. And I'm going to try and keep the screen dynamic. So I have some pictures or photographs or things like that, but I'm also going to be trying to keep the screen dynamic, as in I'll be trying to draw on there, or I might be underlining stuff. So try and pay attention to what I'm saying. Don't get lost in reading the content, because the content is really, for me, as a bit of a visual cue. I want this to be more of a conversation at this point, although I understand that you guys are not able to respond. But what I would like to do is have it as a bit of a monologue, but not have it as so that you're focused on the screen and reading, because then you'll lose the story. So I'm going to weave a bit of a plot for you, and at times it might feel like, oh, he's digressing a bit, but I assure you that I will tie the points together. So we'll do our best for the first hour today, and then what I encourage you to do is send me questions. I'll write down my email address. Let me just turn on this whiteboard here. Feel free to send me your emails if you have questions. I know I'm writing in a bad way, but I'll get better at this. So it's really skhan@spanovation.ca. It's my first name initial, and my last name @spanovation.ca. And we will actually collate those questions, and I think with the next session and all the follow-up sessions, we'll start with answering some of the questions, because a theme is going to basically come out of the different questions that you guys will be asking. Okay, so I'm going to turn off my video now, and I'm going to start talking to you, and hopefully we can have some of this knowledge transfer as best as we possibly can. Okay, so today we want to talk about the fundamentals and design approaches. This is something that I think you need to get used to the idea of thinking about seismic loading in a slightly different manner as compared to gravity loads. So I'll give you some pointers, and because this is a basic course, I want you to understand the underlying principles. Once you understand the underlying principles, it doesn't matter what code you're following. And it also really does not matter whether you're a buildings engineer or a bridge engineer, because once you've understood the bases, the foundational stuff, then it becomes quite easy to go into the application side of things. So today we'll talk about the fundamentals. We are going to talk about some of the allowable design approaches. We've been using the force-based design for quite some time. Now the codes are moving away from it, and the performance-based design is coming in to the picture quite fast. The Canadian Highway Bridge Design Code is one of the first ones that's fully incorporated performance-based design. One of the basic tenets of seismic engineering is capacity design, which I will talk about. So I'll start with some of the fundamentals. We'll talk about the force-based design, the approach. Now there are a few shortcomings in the force-based approach, which we need to be mindful of. And that's where I think the Canadian code comes in quite handy, and it has set the tone for when you can and cannot use the force-based design. So we'll talk about the shortcomings in the force-based approach. We'll talk about the performance-based design approach, its need, and then I'll lay out the fundamental or the general framework for you for the performance-based design. So let's get started. I want you to just focus a little bit on the screen here, and what I've drawn is really a 2-column bridge bend with, say, 4 girders, and the arrows you see is the gravity load from each girder that's transferred to the bridge bend. And I want you to just think back to your second year of engineering, and you'll remember that this is the sort of the bending moment diagram that comes out of this. We've got negative bending over the columns, and then at the middle of the cap beam there is positive bending. The columns are fixed, so they're in double curvature. That's why you see the reversal of bending moment from the top to the bottom. And in terms of axial load, you see compressive force in each one of the columns. So that's, it gives us a pretty good idea as to how we would design this reinforced concrete bridge bend if we were just designing it for gravity. Obviously, in the cap beam, there is negative bending at the end, so your rebar would be at the top, and then you would put rebar at the bottom, and you would reverse the same thing over there. Now, when an earthquake comes along, and I want you to kind of picture this in your head, I want you to visualize and imagine the earthquake as a lateral push on your structure. And when I use the word lateral, what I mean by that is something that could be longitudinal or transverse. So that one word, lateral, encompasses both horizontal directions. So I'm saying, please don't just think of lateral as transverse. Now, if I were to just take a given instant in or during an earthquake, I could think of the lateral push in terms of an applied displacement or an applied force. So let's start by assuming that it's a transverse force. When that happens on this bend, I really get this type of bending moment diagram. Okay, so you can see again the columns are in double curvature. However, the difference is that now the sense of the bending moment at the base of this column is different. It's the opposite of what the gravity produces in this column. I'll call this the trailing column, and I'll call this as the leading column, okay? Just for this direction of force that I'm showing here. Now, when this happens in the cap beam, we see positive bending in the left and on the left-hand side or at the trailing column, and negative bending on the right-hand side. So you can see when an earthquake comes along, and please keep in mind that the gravity is always there. The gravity never disappears. So in order to get a complete picture, you would be superimposing the two bending moment diagrams. And now you can right away see that the bending moments in certain areas, for example, the leading column from the gravity loading and the seismic loading are adding to each other. Whereas on the trailing side, they are counteracting. So on the one side they add, on the other side they reduce the effects of each other. So if my lateral force is large enough, I might get a bending moment here, which is so large in the positive sense that it overcomes this negative bending moment. Now, if I only have rebar at the top of the beam, I have nothing to resist this resultant bending moment, which is now positive or in the other sense. And that used to be one of the classic mistakes that people used to make because we didn't understand the phenomenon that well back in the day. Okay, so the only reason I drew this is to right away open your mind to even show you at a very basic level that the force flow, the way the forces concentrate and flow within your structure as a result of gravity plus seismic loading is different. What you would need to do in this case is also have, in your cap beam, for example, you would need to put positive bending moment at the ends as well, plus at the middle, and you would need negative bending on both sides at the top. Because remember, a small instant later, the earthquake load is going to reverse, and this thing is now going to show the opposite of what is happening right now. The bending moments are going to add on the left-hand column, which is now the leading column, and actually reduce on the right-hand side. Similarly, when I look at the axial force, in this case, I get tension here and compression here. So as a result of seismic plus gravity loading, I'm actually making this side heavier and this side lighter. Okay, so I may end up with a case where this column, if the lateral load is large enough, actually ends up in tensile force. So just keep in mind that things are not the same when we are looking at seismic and gravity combined. Okay, so what we've been very used to as structural engineers is gravity design, and pretty much all of us can turn on gravity, and it acts in a single direction. It acts downwards. It never changes. It never reverses. Our truck loads are always acting downwards, and our design is primarily based on strength. We also use linear analysis when it comes to gravity design, and we don't really account for any cyclical loading. The only obvious exception to that is high cycle, low amplitude fatigue, which we do account for gravity loading, and this is a result of many millions of trucks going over our bridge in its lifetime, and especially if it is made of structural steel, it can run into some fatigue issues. So that's where we look at some cyclical loading. Otherwise, we're not really worried about cyclical loading under gravity effects. And we also don't really rely on load redistribution. So if I have a beam, sorry, this is not being drawn very nicely, but I can actually come up with the elastic bending demand, which looks like that. And I can just design each portion to the maximum demand that it can take and make sure that I have that much capacity and my design is going to be just fine. Now, when it comes to earthquakes, things are a little bit different. Load redistribution is something we should rely on. And I'll talk about that. The one thing I want to really point out here is that if my strength calculation in gravity design is unconservative, that can be catastrophic. So what really that means is if I think that my capacity is 100 units, and it actually turns out that I've overpredicted it. My capacity is only 90 units. And let's say my demand turns out to be 95. Now I'm in real deep trouble. I can have failure of the structure. I can even have collapse. What I want you to just keep in mind, and I'm planting the seed right now in your heads, just keep in mind that that sort of an issue is not as critical in seismic design. And I'll explain why, okay? But just keep that in mind that if you underpredict or overpredict, a little bit in terms of your basic strength, it's not the end of the world when it comes to seismic stuff. There is a bigger issue at hand, which we will discuss, and that leads you straight into capacity design when we get there. So just keep in mind that overprediction of strength in gravity is very is drastic, it's bad. But it's not the end of the world when it comes to seismic engineering. Just park that thought in your head for a second. So an earthquake is a cyclical phenomenon, and unlike gravity, where we do not account for cycles, it's really good to account for some sort of cycling in terms of earthquakes. We do that when we do an actual nonlinear time history analysis indirectly. And as time goes on, we'll be talking about some of those things. Okay. We also rely on load redistribution. And what I would ask you to think about is, again, just go back to maybe third year of engineering and think about just think about the plastic design of a beam. So let's say it's a fixed beam with a central load P in the middle. Right now, I could, as I had done before, design this for just my elastic envelope. But if I were to actually keep increasing this load, at some point, this point would hinge. Okay, it would reach its plastic moment capacity. Then I could increase the load even further, and this side could hinge. And I could have another plastic moment. Now this beam turns into a simply supported beam. But you see, this thing is still not going to fall if my plastic moment can be locked in here and I can have some ductility. If these local areas can rotate, then what I need to do is form another hinge in the middle here to make this a mechanism. And until it becomes a mechanism, my structure is safe as long as I have this MP locked in and the thing is able to rotate. So that's something we call ductility, and I will talk about that in the next few minutes. But really, this sort of thinking is how you need to start thinking about when it comes to seismic engineering. You need to start thinking about nonlinear behavior, thinking beyond the elastic type of analysis, thinking beyond the elastic type of behavior of structures. Okay? Now, if you don't take anything away today, this is the part that I want you to really focus on. I'm going to read it once or twice, and then I'm going to tie it with the point I've made previously. So previously, we understood that it's not as important, the fact that we might have overpredicted our basic strength in seismic is not as important. In gravity, it's very important. What is very important in a seismic environment is what I describe as, or people have described as, overprediction of design strength to be less important than under prediction of overstrength capacity. It's a mouthful, I understand, but if you just stay with me, I think I will be able to explain this to you. So previously, for seismic or for gravity, we were thinking about not over predicting the design strength. But what I'm saying is it's less important than something else. It's the under prediction of overstrength. Okay, and we will talk about that. So just remember, maybe even write it down, but I will come back to this. And this really forms the basis of capacity design, which is very, very important when it comes to seismic engineering. So we don't want to do some under prediction. Just keep that in mind. Over prediction for gravity is bad, and some sort of under prediction is bad for seismic design. Okay, we will come back to this. Okay, so here is where I would like to talk to you about the sort of the basic phenomenon as to what's going on when we do seismic design. What I have here is a system which is fully elastic, and an earthquake comes along and pushes it, imparts some sort of force and displacement to it. Okay, now I want you to just park one more little thing in your minds. What I want to say to you is start thinking about the earthquakes, the seismic phenomenon, primarily as a displacement demand on your structure. Forces are very important, and as structural engineers, we are trained to think in terms of forces. What I'm going to ask you to do is keep that thinking in your mind, but put it aside for a little bit and start thinking of an earthquake as a displacement, something that the earthquake is going to do to your structure. It's going to be a displacement demand. The force we can control as engineers. So here's the thing. What I have is an elastic system, which is shown by this straight line, which I haven't drawn very straight, obviously. But the earthquake comes along and tries to push your structure to this displacement value, delta U. Now I say, okay, I don't want any kind of damage in my structure. And if I don't want to have any damage in my structure, I better make sure that it is strong enough and stiff enough that it does not lose its stiffness, it does not lose its strength. So the line that's drawn over here as system 1 line, which is a straight line up and down, has the same slope. This is an elastic system. Now remember, to make sure that this system does not have any issues in terms of damage, I have to have the strength F1y in the system. So I have to design it for this force value, this much strength. And that may mean that my sizes are really large, my structure is really ginormous. And also what happens in that case is you end up spending a lot of money. And we know that without money, nothing will happen in the world. This, at the end of the day, you're developing a piece of infrastructure. And as engineers, we want to optimize our design. It's not the best approach to design everything elastically with big sizes. And the issue is not just the economy of the structure. There are other issues that come in, which I will talk to you about. Okay, so what I say is I'm not going to design this structure to stay elastic and have no damage and have it so strong that it reaches that point. What I'm going to do is make it weaker. I'm only going to design it to have it this much strength, and that is F2y. Now, we've done lots of analyses, lots of nonlinear analyses, and people have seen that for a certain period range, and this is particularly true for bridges, somewhere between 0.5, 0.6 seconds and up, or from 0.5, 0.6 seconds up, the equal displacement principle generally holds. So whether I design this bridge or this structure for this force level F1y or design it for F2y, my total displacement demand is going to be this much, which is delta U. Okay, so I say, well, how can I design this intelligently, have some controlled, contained damage, but make sure that my structure behaves properly? What you really need to do is have your structure so that it's able to get to this displacement level. And that's why I was emphasizing the point that an earthquake is really a displacement demand. So if I reduce the strength of the structure, I only design it for F2y, now as long as I meet this displacement demand, I'm going to be okay. The trick is that I have to be able to travel, or my structure has to be able to traverse this path. I'm going to call this the elastoplastic path. This is a bit of a generalization. Real structures usually are not fully elastoplastic, but to illustrate the point, this is where we're starting. So the big thing is, can my structure, once it becomes plastic, can it traverse this path and just keep deforming and reach this point so that I can meet my displacement target of delta U? And as long as I can go along this elastoplastic path, I'm okay. The penalty I pay is a bit of damage, because this line, this flat line, this plastic line, means I have some damage in my system. Sorry, I was now doing it with my mouse. So this really just means that you need to have some control damage, but if you can get there, you're going to be okay. Now, the way we design things is obviously not for this total force. We design things for this lower force because, one, it's more economical. We know where the damage is going to be. And if a larger earthquake comes along, all that means is that in this case now, where my structure was going to go to this point, a larger earthquake comes along, well, I cannot develop more force than this. It's just going to put more displacement demand into my system. Okay, so my force is capped. My displacement might be a little bit more. So one earthquake, a smaller earthquake, may push it to delta 1. A larger earthquake is going to push it to delta 2. In this case, if my structure is really strong but has no ductility, i.e. it cannot travel along this line, well, guess what if a large earthquake comes along and tries to push it further? I'm just going to fail at this point. So I haven't really done a very good design by putting too much strength in it. So remember, strength without ductility is really futile. Strength is an important thing. Ductility is more important. And our design has to be done in a rather sane manner based on these sound principles. So we don't always go for no damage. And that's why I say to people, never use the term earthquake proof. We haven't invented such a thing yet. We are designing earthquake resistant structures, and that's a very good thing. But on purpose, we make certain parts of our structure weaker, and we know where those parts are going to be, and we know that those are the ones where the damage is going to occur. Okay, and then we do something with those parts of the structure to contain that damage. And those areas of your structure now act as fuses, because this force cannot go beyond this level. It cannot just keep climbing up. And what that does is it saves the rest of your structure from force overload. Okay? And I will explain that point in a bit more detail as we move forward. So let's go forward a little bit. I've basically described this. Okay, so now I'm going to read this. So we design the structure not for the elastic force level. We design it for a lower force level, and we make sure that the system can respond in the nonlinear range. And how it is able to respond in the nonlinear range is because it has ductility. Okay, and here is a measure of ductility. Look, I have some bent, some bridge bent, and when I start to push on it, you see this first line is straight because it all stays elastic. Then something happens. Some part of it becomes plastic, just like I was drawing before. The hinge or the beam that we looked at became plastic. Now at that point, the structure becomes a bit weaker, so its stiffness then gradually reduces. So I form a second hinge, I form a third hinge. And by the way, a hinge is nothing but except when the local cross-section reaches its moment capacity, okay? So if as soon as my first hinge forms, I'm not basically just destroying my structure. If I can keep forming those hinges at different points, and the hinges can keep operating properly, i.e. they don't just disintegrate, and we'll talk about how to design those hinges to keep them functional, then I've done a good design. So you see my structure is only elastic to this point, and beyond that it's curving and it's weakening, but it's able to displace this far before one of my critical hinges fails due to some reason. Okay, I'm saying it's a ductile failure of the flexural hinge, and that's what we want. And some of these terms will become more clear as the course goes on. If you haven't heard these before, I'll try my best. But really, I'm just trying to show you that this is the ductility in the system. Now, if all your system was able to do was in the force displacement curve come up like that and just break there, that would not be a good design. I want you to think back to the stress strain curve of rebar. Okay, so we go up, we form our first yield, then we have a yield plateau, then we have strain hardening, then we have strain softening and necking, and that's where we break. So this material, after it becomes inelastic, has a lot of ductility. Contrast that with cast iron. It goes up and it breaks. You don't want your structure to do this like cast iron does. You want it to behave like this so that you're able to get this sort of behavior. Okay? So strength is good. We need to have some basic strength in the system. Beyond that, you are looking to have ductility in your system. Okay, so let me just have a look and see if I've explained everything. You can have a look at this bit of math, but what it really shows is that the factor by which you reduce this force level down based on the equal displacement principle, that's the amount of ductility you need to have in your system. So the more you reduce this force, if I were to only design it for this force now I need more ductility in the system. You can see that my ductility here is larger than this value. Okay, so I can reduce the force. That's why I keep emphasizing, think about the displacement. Displacements and deformations is where the understanding has gone. That's where we are able to do sound designs. That's how things come about in a much better manner when it comes to seismic design. Force is important, but beyond that, we want to be able to think about deformations and displacements. Okay, so I've kind of described this. The basic idea is that we make certain parts of our structure purposefully weaker. Okay, we don't design for large earthquakes, in large earthquakes for our structures to stay elastic. We want to make our structures somewhat weaker. That brings about economy. That also helps with some design issues, which I will describe. So these fuses behave within certain bounds when using performance-based design, and we'll come to that. But really, a fuse or a plastic hinge, and a plastic hinge is not the only, or a flexural plastic hinge is not the only fuse known to us. There are other ones, but really, it needs to have stable hysteretic behavior. So here, I've drawn a moment rotation curve under cyclical loading. So I go up, and then something yields here, and then it yields, and the earthquake reverses its direction. Now it comes down, and now it yields on the other side, and now the earthquake direction reverses again, and you start to see these loops happening. Well, as long as you can keep these loops going without your section just rupturing somewhere, you've done a good design. And remember, the area under this graph is the energy, the earthquake energy that you're dissipating. Okay, so the fuses have to be such that they're able to dissipate energy. Okay, so they need to have stable hysteretic behavior. If we have something like this, which goes up and yields and goes up, and in the second cycle just flattens out, reduces its strength a lot, and then in the next one it just breaks here, that's not a good fuse. You haven't done a good design for that portion that you've made purposefully weaker. Okay? Okay, so now what happens with these fuses? How do they help us? Why do we do this besides the fact that there are some economic advantages? Well, here's what it is. It restricts the force that gets into the system. Okay? I'm going to skip ahead, and I'll come back to this slide in just a minute. So I had let's just go back here for a second. Just bear with me. Okay. So the idea is that we make all elements except the structural fuses resist maximum seismic forces in an essentially elastic manner. So it's just the fuses, it's just these parts of the structure. So let's say I have a bridge bent. My fuses are usually at the top and bottom of the columns. And what happens is, as I draw the force displacement graph, I go up, my first hinge forms, my structure flattens, the second hinge forms, the third hinge forms, and the fourth hinge forms, and then I have a mechanism. Now, I cannot have more force in the system than this. I design this cabin and the columns outside of the plastic hinges, my foundations, everything else is designed such that it stays elastic. So the only plasticity that's happening in the system is basically concentrated within these fuses. So when a larger earthquake comes along, this force is unable to grow. It's unable to go beyond this point. The only thing that happens, as I was describing before, was the displacement increases. So really, they act very similar to our electrical fuses. So think about an electrical fuse. What happens if there's an upsurge in electricity in your house? So let's say that you've got a refrigerator or a very expensive television, and it can only take 100 units of electricity, 100 amperes. I'm just picking a number. If you have not set up a fuse or a circuit breaker in the system, and if there is an upsurge and you get 110 amperes, well, what's going to happen? Your refrigerator or appliance is going to burn. Okay, it's not going to be functional. If I have a fuse, the fuse is going to be destroyed. The fuse is going to stop functioning. It's going to stop sending any more current into the system, and it's going to save your fridge or your appliance at the other end. the idea is very, very similar with seismic engineering, with structures, because we don't know how big of an earthquake is going to come along. And also predicting the forces and displacements that are going to happen as a result of an earthquake is, yes, it's scientific, but it's still something that has or carries a lot of uncertainty in itself. Okay, so these fuses, they provide an upper bound on the force that needs to be resisted by the system. That's why they're very important. So imagine if your column is 1 meter in diameter and it has a certain bending moment in it. Now my earthquake comes along and it increases that bending moment from gravity, and it pushes it all the way to its limit. So now it's formed a hinge. How much force do you think is going to get into the foundation and the cap beam after all 4 hinges have formed? This much. Okay. So now I can design the cap beam and the foundations and the joints to be stronger than the demands that come in with respect to this force level. Now, if a larger earthquake comes along, it only puts more ductility demand into my fuses, and the fuses save everything else. The fuses save my cap beam, they save my columns from shear failure, they save the joints from failure, they save the foundations, which may even have piles. So that's how these fuses help us. If I go with very large sections on my fuses and a larger earthquake comes along, what's going to happen is my fuses are now going to generate more force. Now, to protect my cap beam and my joints and everything else, I am going to have to make them bigger and stronger. So in a way, I'm starting to chase my tail around. I'm starting to go in a vicious cycle where I keep increasing the sizes of my fuses to keep everything elastic. And now the sizes everywhere else are starting to go up. So that's not the best way to design things. Okay? So what we do is, just to bring the point back, we design weak columns and strong beams and bridge bends, which means our columns are the ones that form the hinges. The beams are stronger than the columns. There are link beams and eccentrically braced frames. So here you have an eccentrically braced frame, and in between this, and by the way, this is eccentrically braced because the braces do not come to the same point. They are eccentric to each other. This link yields in shear and caps the force again that goes into the columns and the braces and the cap beam. So now you make sure that this thing can dissipate the energy. This becomes your fuse. This has all the ductility. Everything else can just be designed elastically. Okay? Okay, so let's move forward. I think I've described this. You don't want your non-ductile elements, which are the cap beams, the beam column joints, the footings, the column joint, the column footing joints, and your superstructure sitting on top to form any kind of hinges. Okay, you want to contain that to your columns in this case. Okay, and we only want flexural hinges to happen in this case. So flexure is our friend in this case. We don't want any shear failure because we will not have detailed anything for any kind of real shear failure. When it comes to eccentrically braced frames, yes, that's a shear driven system, and we actually design this shear link with a lot of stiffeners to make sure that this can yield in shear. Okay, so I think and I hope that you're getting the idea here that we make certain parts weaker, everything else has to be stronger. Now, let's come back to the point I was making earlier. So we said that if we overestimate our capacity for gravity, that's bad, and we understand that. That's not the case when it comes to seismic, I had said. So this is a system which was much more strong. Okay, so I want you to focus on this diagram for a second. This would have been the elastic demand in the system if I had just designed it elastically. I'm assuming it has some ductility, so I've drawn this horizontal line. But I'm not going to design the system for this much. I'm going to design it for a much lower force value. Okay? Now, whether I predict the strength to be here or here, it doesn't really matter, because all that means is a very small change in my ductility demand on the system. Okay, so for this higher line, my ductility demand is this much, and for the lower line, my ductility demand is a little bit higher. So overestimating the flexural hinge capacity is not that big of a deal. It just simply implies a higher local ductility demand. Now imagine that you have underpredicted the overstrength. Okay, now we know that structures usually have overstrength in them. So if you were to take a concrete sample and crush it, and let's say that its strength was supposed to be 35 MPAs or 4 KSI, if you give it 56 days or you give it 2 years, in all probability, it will be 25-30% stronger. If you take a piece of reinforcement, which is 400 MPAs or 60 KSIs, and you put it in the machine and you do a tension test on it, you'll find that it'll be 10, 15, 20% more strong than what you've designed it for. So now what's happening is, because of this material overstrength and the fact that, you perhaps have pushed the system quite far, your steel has now gone into strain hardening, your fuses are actually stronger than what you assumed them to be. So rather than your basic curve sitting here and you designing everything for cap beams and joints and everything else to stay elastic for this force level, you should have designed it for this force level, because your structure is actually stronger by this much. Your fuses are stronger. So the analogy that I had before, I want to bring that back into the picture. So let's say you thought your electrical fuse could take 100 amperes, and your fridge, had a certain margin, and let's say it was matched to 100 amperes. Now, if you have an upsurge, and for some reason, maybe the wire is too strong or something, it lets 110 amperes pass through it. What do you think is going to happen? The electrical appliance is going to fry, because your fuse was too strong than what you had thought it was. Same thing applies in this case. If you think your structure's maximum force level is this much, but it actually is higher, and you have underpredicted it, what's going to happen? You may not have the flexural hinging that you expect to happen. You may have some shear failure, or you may hinge the cap beam instead of hinging the column. You may actually also hinge the beam. Now, the beam has not or will not have been detailed for any kind of ductility. It will have been detailed to stay elastic. Your footings, your piles will see more force because your column here is stronger. You may not have designed these for that higher force. So what's way more important in terms of seismic design is to not underpredict the plastic hinge overstrength capacity. Okay, so the codes lay a lot of emphasis on that. So please keep this in mind as we move forward in our thinking and our understanding. And this is clearly what happens when things are not detailed properly. So you can see in this figure, very few ties. I think we used to put number 3 ties at 12 inches, which is probably 12 M's at 300 when I'm speaking metric. That did not confine your plastic hinge. They did not give you any kind of shear capacity. So you couldn't really form a flexural hinge. You ended up with this sort of a behavior where your fuse has really just given up. The last difference, the one difference I want to point out between an electrical fuse and a structural fuse is this. An electrical fuse will be destroyed and it will save the appliance. In our case, the electrical fuse has to keep operating at that force level. So that force M, or the bending moment M, all of that, it has to be locked into the system. It cannot behave like this, because if our fuse is not able to keep operating at that force level where it's hinged, where it's formed, then we're going to have structural failure. So that's one difference that we need to be mindful of. Yes, we form hinges, but we have to contain the damage, and we've got to make sure that the gravity load flow and the seismic load flow at that level keeps happening through our fuse. We cannot have it just get destroyed. And that's where good detailing comes along. Okay, now I see that I'm coming towards the end of things. We've got 8 minutes left. I made a little mistake. I was supposed to have a slide here just to give you some homework. I would like you to go to our Spanovation Bridge and Seismic School YouTube channel and watch a couple of videos on there. There's a video there about the deficiencies, the typical deficiencies of a two-column bent. If you just Google Spanovation Bridge and Seismic School, you will find our YouTube channel. Please subscribe, it's completely free. Some of the things I'm talking here, you'll find snippets of those, and some of those other videos. Will be putting in a lot of content, a lot of free content in the coming weeks. And we have a course coming up which is going to be on the conceptual design of bridges, context-sensitive conceptual bridge design. So we're going to be talking about how to conceptualize a bridge when you have certain constraints. So that's going to give you some real-life examples of how to do sizing and how to come up with different alignments and all of that. In the next lecture, I will have that information for you handy, and you can go and you can also go to our website. If you go to www.spanovation.ca, and then you can look at the courses that are coming up. Okay, so far, some of the things that I've talked about are, we still do our seismic design based on a force-based approach. So what we do is we say, okay, my elastic force level would have been this much, and I am going to design it for this much. Then what I do is I only put this much strength in my system, and then I detail it according to the code so that I make sure that I have this much ductility, and my design is done. I never go and check the actual displacement or deformation capacity of my system. So it's still keeping very much in line with how we think about the design of structures in a force-based manner. But there are some principal shortcomings of doing our designs this way. It ignores the interdependency of strength and stiffness. And the next slide, I have some photographs that I will show you, and things will become more clear. The ductility capacity and the R factor, we have no consensus among codes internationally, because there is variability in how we define yield and ultimate displacements. Okay, so we saw that the R is equal to the ductility value. Okay, and if you look at some of the codes, or all of the codes for different systems, they'll give you the force reduction factors, which basically tell you how much to reduce the force level from the elastic level to the design level for different systems. And it's all dependent on how much ductility we think we have in a given system. So a shear wall has a certain value. In our code, a single column bend has an R of 4. A multi-column bend has an R of 5. Okay, but you can imagine a 2-column bend and an 8-column bend. perhaps having the same R value is not the wisest thing to do. However, this is how the force-based system or design works. I also want you to think about system ductility. We'll quickly talk about that in just a minute. And the most relevant is that I cannot, with any reliability, define different performance levels or quantify different performance levels. I cannot tell my client or my fellow engineer how my bridge is going to be behaving and what at the end of the earthquake is it going to look like. What is its performance going to be? Am I going to be able to put it, am I going to be able to put some emergency traffic on it? Am I going to be able to put all kinds of trucks on it? Am I going to have to completely shut it down? It's very difficult using the force-based design to do that. Okay, so this is our assumption, really. We think that when we make something stronger, so this is a moment curvature graph, but you see this thing goes elastic, plastic. I make it stronger, it goes up more, goes plastic. The issue is that in reality, that's not how things work. When you make things stronger, so if I go from a column of a certain diameter to a wider column, I also increase the stiffness. So even though my bending moment capacity is increasing, so is the slope of this line coming up. Okay, and in force-based design, we pretty much don't take account of that. Now, before I close today, I want you to think about this. This is a system with a medium height column, a very long column, and a very short column. Okay, and if I were to draw their force displacement curves, the shortest column, C, is sitting up here. It has the least amount of ductility because it fails here, has this much ductility. The mid-height column is less strong, but it has more ductility. And the tallest column, or the longest column, is the weakest, but it also the most flexible and has most ductility. So now that we understand the definition of ductility, it's this displacement divided by that displacement, and the R is equal to mu. You can see that if I use the same R value, for this bridge everywhere for each column, that's not a consistent design, because you can see inherently their R values are different, their ductilities are different. So force-based design, when it forces us to take a blanket R value and apply it to all our substructure elements, so in this case, if it's a single column bent, I use an R of 4 for all 3 columns. That is simply not appropriate. That's a big shortcoming. It will give me an inconsistent design. It will give me an inconsistent level or margin of failure between different elements. Okay, so I want you to keep these things in mind as we move forward. Now, this is a graphic from NCHRP Synthesis 440. Okay, and this is something that I want you to just see. Again, this is showing a force displacement curve, and now we can see the different performance levels. Okay, so the first one is basically essentially elastic. It has some little bit of cracking at the base. Once the earthquake goes away, this thing is going to straighten back out. These things are going to close, and we can put all the traffic on it. We're fully operational. Beyond that, you get some weakening or softening of the system, the rounding off of the curve. Now you have more cracking. You get to this point, you're still operational. You might have to send somebody out there to inject those cracks. This thing is going to come back most likely. More damage happening. Now you've got some general spalling and extensive cracking. You're moving along this path. And then you reach a point where, you're beyond which you're going to start to go on the negative path here. Okay, that's not something we want to ever design for, because an earthquake will come along, there may be an aftershock, and with negative stiffness, it's not going to be a very good thing to be designing for. Okay, so with performance-based design, the moral of the story is that we can actually figure out this whole range of structural performance. We can define where my structure is going to be sitting. So I could say after an earthquake, I'm going to be sitting somewhere here. So really, I don't need to do anything, or I'm going to be sitting somewhere here. Now I need to have some intervention happening. Okay. So I think you're getting the idea here. I'm going to stop. We are out of time. I'm going to pick it up right here next time around. In the meanwhile, if you have questions, please send them to us. I've set the stage for performance-based design. Remember, none of this can be done by doing force-based design, so we can't really quantify the structural behavior and the performance at the end of our earthquake. So this is where I'm going to stop. Please send me any emails that you might have. We're going to pick it up. I might go back a slide and start from there. Again, my email address is skhan@spanovation, which is spelled SPANNOVATION.ca. And I will definitely talk to you next Friday, same time, 9 a.m. my time, which is Pacific Standard Time. And wherever you are, please stay safe, practice social distancing, and keep making yourself stronger and better. And I will talk to you next week. Bye for now.
Thanks for watching this free webinar by the Spanovation Bridge and Seismic School. Here's a couple of calls to action for you guys. Please join our mailing list for our upcoming online courses. The first one being the context-sensitive conceptual bridge design. You could do so by going to www.spanovation.ca/school. This will keep you updated on early bird offers and the course release dates. And also, would be great if you go and subscribe to the Spanovation YouTube channel as we try to put up new content on that on a regular basis. And so a lot of the support videos to this particular seminar, which is the fundamentals of seismic design, you would be able to find on our YouTube channel. So feel free to go there and subscribe to it. And once again, thank you very much, and we look forward to seeing you in the upcoming free webinars.